Hi, I'm Paul Schmitt. I'm a research scholar at Princeton, and today I'll present PGPP, or Pretty Good Phone Privacy. This is work done in collaboration with Barath Raghavan at USC. So the issue that PGPP is working on is that the phones we all carry in our pockets are actually tracking our locations at all times. And this is because cell networks need to quickly reach you if you have voice or SMS or data. The issue is that carriers are selling this information to data brokers who then sell that information to basically anyone. So we've had these stories like we have on the right here, where with just a few $100s and a victim's cell number, you can get real-time information or even 5 years of their location data based on this fundamental recording and leak of location information in the cell architecture. So what can we do? Towers need to know how to talk to phones and where the phones are. And so is this an impossible problem to prevent? So I think it's useful to step through some of the identities that are in the cell architecture that are used and abused by attackers. So first we have SUPI and IMSI. SUPI is the 5G equivalent of the IMSI, if you've heard of the IMSI in the past. And these are really important identifiers because they're permanent identities, they're burned into your SIM card, and they're globally unique. So these are really popular for attackers with things like IMSI catchers when they're trying to establish where a person has been, because they're essentially a one-to-one correlation between the user and their IMSI or SUPI. Now, networks realize that SUPIs and IMSIs are really sensitive information. And so once you attach to the network, they will often give you a GUI, which is a temporary replacement for a SUPI or IMSI. And so they'll periodically refresh that and change that so it's harder for people to track. Although prior work has shown that there are some GUI replacements that haven't been the best in the past. The refreshment strategies aren't as robust as they maybe should have been. Maybe the randomization strategies could be fixed. However, GUIs are the temporary replacement that people use. Now, 4G LTE and 5G are both IP-based networks. So once you establish connectivity, you're handed an IP address. That's typically a NATed DHCP address from the gateway that you're connected to the rest of the world. And attackers have used that in the past from the outside to correlate web traffic and other activities of user traffic to a given NATed IP address. And then lastly, there's the radio identifier, which is the L2 connectivity between the handset and the tower that's connected to. People have used that for really fine-grained location information based on essentially timing information. So where these are all located we have RNTI is in the RAN, the radio access network. In the core, we have the SUPI, IMSI, and the GUI, and then the IP address is at that gateway. And so what PGPP is focused on is really that SUPI or an IMSI and decoupling that from your identity, because those are the permanent identifiers that never change and are abused quite a bit in the real world. And so what happens with conventional networks, the issue is that connectivity, billing, and authentication all use those same credentials, and they're all sent to basically the same location in the core. And so this design is based on this prior trust that occurred in the network, where we all just assumed everybody participating in the cell core is trustworthy. However, we know that's not the case anymore, and so we need to do something to fix that. Now, you may be thinking, well, doesn't 5G encrypt the SUPI when it's sending it to the backend? And that's absolutely true. So eavesdroppers are thwarted by 5G's encryption. However, even though you've got this encrypted tunnel to the core itself still knows the actual value. And so the carrier is always going to continue to know exactly where each user is and their individual ID. And additionally, 5G has really been pushing towards smaller and smaller cells for reaching lower latencies and higher throughputs. And that means that the carriers have more and more fine-grained location information for users, whereas in the past they had maybe just macro cell level location information. Now they know to a very small cell level where you've been located. So 5G can actually make things worse. And so in the paper, we define two types of attacks, bulk or passive attacks versus active attacks, which I'll get to in a little bit. And bulk attacks are really the things you may have heard of in the past, where they're really just using that SUPI and IMSI to identify you as you move through time and space. And so these are things like IMSI catchers. Law enforcement uses a device called a Stingray, which is just an IMSI catcher. You can use $25 SDRs, and you can listen to IMSIs and SUPIs that are broadcast in the nearby area. If you're at a higher level where you have a more global view of the network, you can have carrier level logs or government surveillance where they maybe have multiple carriers where they're tracking all of this data. And so we've got this issue of bulk attacks are just generally prevalent in cell ecosystem. So PGPP, our goal here was to completely remove trust from the carrier itself. And so what we wanted to do was decouple connectivity from billing and authentication in the core. And we moved billing and authentication to a gateway that we've designed called the PGPP gateway that sits between the core gateway and the rest of the internet. And essentially what we do is we leave connectivity alone and we nullify the value of the IMSI by issuing everybody in the PGPP network the exact same IMSI. Now, what happens is when you first attach to the network, you send that IMSI to the core, and we've listed that single IMSI for basic connectivities, which means you're going to be handed an IP address. And at that point, with your IP address, you can connect to our PGPP gateway and use an oblivious authentication protocol that we've designed, which is details are in the paper, which essentially acts like a captive portal in the background. We don't want users to actually interact with it, but it can just happen as a background process. And you can exchange, you can offer tokens that you've purchased without offering your identity. We don't need to have your IMSI or your SUPI along with those tokens at the PGPP gateway. All we see is your netted IP address. And at that point, we've successfully separated, but we can still bill and authenticate users in a way without knowing their ID. And so from a carrier perspective, what we see is where today you can see every individual user and identify them, with PGPP, all users are indistinguishable. And so as you add more users, you've got additional anonymity because it's very hard to really understand who's who in the network. Now, the other type of attack that we talk about in the paper are active attacks. And these are paging-based attacks. So pages are the mechanism in which the carrier finds you quickly. So if you've got this incoming voice or SMS, they need to locate you. And what they do is they essentially create broadcast domains based on adjacent cells in their network. And these are called tracking areas. So we see here on the map, we've got 3 tracking areas, red, blue, and green. And this is used to minimize mobility overhead. So as you cross between sets of tracking areas, you will incur additional overhead because you're basically telling the network, I've moved to a new tracking area, and it changes where the broadcast domain is for that user. And so in idle mode, the carrier actually doesn't know where you're located. And so what they do is page the entire area for you. So attackers have used this in the past, and they can send a call or Facebook message or WhatsApp to a target phone, and it will be broadcast. And since everybody generally knows those tracking area boundaries, it's easy for an attacker to say, okay, now we know where this user is located. So with PGPP, we wanted to do something about this. And so we do this by using a concept called tracking area list, which was added in later stages of 4G LTE and is now present in 5G. And we do this, we essentially randomize and increase the broadcast domain. And so what this looks like is we use this thing called a tracking area list, which is a bottom-up view of the network where each UE or each phone is handed a list of tracking areas that it can use and travel through without causing overhead of mobility caused overhead. However, what we do is we essentially randomize for each UE. So rather than using the existing tracking areas that are top-down defined by the carrier, as each UE shows up, we can randomly build tracking areas for that user and then send them using this tracking area list. And that way the attacker has no way a priori of knowing exactly where a victim is located. Of course, the trade-off of this is that we're going to have much more tracking area boundaries for mobility. So, and when you cross those tracking areas, that can actually cause quite a bit of control traffic compared to traveling within a tracking area. And so to understand this, we simulated this in the network. We did a simulation based on LA County and an LTE network of existing infrastructure that we know, and we simulated pedestrians and cars and simulated traffic. And so we could see as we increase the TAL length, which is essentially increasing the broadcast domain, we're increasing the control traffic because more and more towers are broadcasting pages looking for users that probably aren't located near them. And so what this means is for paging area anonymity is you're drastically increasing the area in which the attacker could believe the user to be in. And so we draw a bounding box and calculate the area of the broadcast domain. And we can see with even just a small tail length increase of say 4, we've drastically increased the area in which the victim could be believed to be within. However, as we increase those lengths, the size of that broadcast domain, of course, we reduce the capacity of the network because we're incurring this broadcast traffic or this additional control traffic. So what we have to do is we need to change the map. And we detail this more in the paper, but essentially this is an LTE network in the Los Angeles County area, and this is their existing tracking areas. And what we can do is regenerate based using k-means clustering, different size tracking areas. So number of small tracking areas, small number of tracking areas that are very large, all the way up to a very large number of tracking areas that are generally very small. So that's 1,000 tracking areas that are very small. And we can see as we vary this, we can start to approach the amount of control traffic that conventional or the standard network incurs. But we still have the great paging area anonymity, even as we have a huge number of tracking areas that are very small. So with 1,000 TAs, we still get a large gain in broadcast anonymity. And again, as we do that, we then begin to approach, again, that user capacity that we originally had with conventional. And so there are a lot more details in the paper. I hope everybody reads it. And please send me any emails if you have any questions, and I'd be happy to take them. Thank you.